Right, so hello everyone, I'm Jovan. I'm a PhD student at the University of Cambridge, and I will be talking about generalized rewriting. Um, so, for some background, in my work, as Joachim said, I work on writing tactics, and in general, I try to sort of make the lean user experience better. Unlike the Fro, I try to focus on making mathematicians happy. So this includes tactics, interactive tactics as well, so point and click, elaboration, de-elaboration, and performance improvements, like making the sim tactic twice as fast. Various different things that are metaprogramming. So in this case, the generalized rewriting tactic. So it's a variation of the rewrite tactic. The sort of interface is the same as the rewrite tactic, but instead of rewriting with equality, we rewrite with some other relation. So this can be an ordering, so less than or equal to. It can be congruence modulo n, but it can be many more things. You can have set, subset, implication, divisibility, almost everywhere equality. And so I think the best way to show this is through some examples. Because this might sound a bit confusing. Right, so I prepared some examples here. So sort of the motivating example for this tactic, in my case, was ordered rewriting, where you have a less than or equal to relation. So here we have some example where we are adding some numbers, and we have some ordered goal, and so we want to just use the b is less than or equal to b prime hypothesis to change b into b prime, and ta-da, we can just change b into b prime. And so another example is rewriting modulo n. So there's been quite a bit of friction with people trying to use congruence modulo n, because somehow the fundamental thing you want to do with congruence modulo n is you want to rewrite with it. But if you don't have a generalized rewriting tactic, then this reasoning doesn't work. So here I can show we have a congruent to b, so we can turn a into b, and we can rewrite the other way as well, just like with normal rewriting. Now for set containment, we have here some goal with a set subset and some union, and again it's like if we make the set b bigger, then the statement becomes a stronger statement. So we can do this replacement. We can replace b with b prime, and this is a valid tactic step. And our goal doesn't actually need to be a relation itself. You can do, for example, a goal of non-emptiness of a set. So if you want to prove that b is non-empty, you know that a is a subset of b, then it suffices to show that a is non-empty. So we can rewrite like that as well. And here's an example just to show how everything can be put together. We have a non-emptiness of some set constructor of some x's at most 2 times b plus 1. So if we make b smaller, then 2 times b plus 1 becomes smaller. And so x less than or equal to that number becomes a stronger statement, and you can sort of keep going with that reasoning, and this works.
What happens if you rewrite the other way?
If I rewrite the other way, so if you mean like if I turn the b into an a and I try to rewrite. So we will get some error message. It says the tactic could not discharge b less than or equal to a using a less than or equal to b. So it figures out exactly which relation it would expect there, and then compares that to what you gave it and tries to match it up. And if it doesn't work, then it tells you. Right. And here's an example that some of you might have seen in a talk a few days ago, the S combinator, where in that talk there was actually given the example of this particular rewrite. So we can rewrite with an implication. We can use A implies B, to change this B into an A, like this. And we can't use grewrite here. I'm using a different name tactic because grewrite will think that A is like a hypothesis, and then it'll complain that B is not a relation. So in this case, there's I called it apply rewrite because it's sort of half rewriting, half applying. And it can also do sort of a normal apply. So H1 applied to the goal here. It treats the first A as a hypothesis, and then it treats A implies C as a relation. So it turns C into A with the extra side goal of A. Right. So I've shown you some examples of what it can do. So, well, how does it work? So the implementation is based on the gconger tactic. It's sort of using the features of the gconger tactic. This tactic already existed in MATLib. It was implemented 2 years ago by Heather Macbeth. Sorry? Oh, and Andy. Okay, sorry. And by Mario. Right, so this is a generalization of the conger tactic. So if you have a goal where you have two sides related by some relation, then it sort of applies lemmas that are of that form to reduce the goal. Yeah, so here's an example of what that means. We have here a goal A plus C is less than or equal to B plus C. And then we have a gconger tactic, which turns that into just A less than or equal to C, B. Up?
We can't see that because you're close.
Oh, sorry. Yes. And so what does the tactic do? It sort of recursively finds the right generalized congruence lemmas. So in this case, we have this lemma add right, which says exactly the thing that we're proving here with the gconger tactic. And it will also automatically sort of fill in the goal. So if I add an extra hypothesis A less than or equal to B to the environment, it just solves the goal entirely. It just finds this hypothesis. So how does grewrite work? So if you have some goal and some relation A is related to B, and you want to change A to B in the goal, so the first step is the same as in a normal rewrite tactic. You first figure out where A is, and you construct the term that you get by replacing A with B. But now instead of proving that those two things are equal or equivalent, you prove that one implies the other one. So if the goal is P of A, and you want to replace it with P of B, you need to prove that P of B implies P of A. And this is a goal that can be solved by the gconger tactic. Because implies is a relation. So this is actually a feature that didn't used to be there in gconger that I had to add in order to make grewrite work. So gconger can now support implication. And so we have also specialized implication lemmas for gconger that do this for us. And of course, if we are rewriting at a hypothesis, I didn't show examples of it, but you can rewrite at a hypothesis, and then the implication has to go the other way around. You have to show that the old expression implies the new expression. So here's an example. So grewrite can change this B into a B prime. So what is actually happening? Rewrite under the hood creates the following goal, runs gconger on it, which then finds some lemmas to apply there, and solves it, and then it just applies this thing to the goal, and we can see that B has been replaced with B prime. Right. To see sort of what sort of proofs grewrite creates, here's a kind of example we had earlier. And so basically what is being generated is a proof that is a composition of a bunch of these gconger lemmas or monotonicity lemmas. So first we have the monotonicity of non-emptiness. So this just says, okay, s.empty implies t.empty if s is a subset of t. And so here's one that says, sort of this congruence rule for the set builder. And we keep going with these lemmas. And here is a subterm proving that, that 2 is greater than or equal to 0. So this is important for the multiplication. You can't always rewrite inside of a multiplication with an ordered rewrite. You can only do it if one of the sides is non-negative or maybe positive. So this is automatically discharged by the tactic. And if it can't discharge it, then it'll give an extra side goal that you can then try and prove yourself. Right. So lots of things were already tagged with the gconger tag in MATLib. And I added a bunch of more ones to support more uses of grewrite. And if you want to use it on your own relation or your own definitions, it's very easy. All you need to know is the gconger tag. You put it on all of the generalized congruence lemmas. For transitive relations, you can also use an istrans instance, and this is all you need to do. So here's an example of something that's currently not yet supported in MATLib, but could be if we added the right gconger attribute. So we have here some goal, A is congruent to B modulo n, and we have a hypothesis that n divides m. So what does this mean? So if something holds modulo n, then it must also hold modulo m, because somehow, sorry, the other way around. If it holds modulo m, it must hold modulo n, because modulo n is somehow sort of doing more modulus. So if I add this attribute to gconger, the following rewrite is actually possible. And I'll conclude the talk with an example that someone posted on Zulip. So not too long after this tactic was implemented, someone came to Zulip and said, hey, I have this lemma. I'm trying to prove distributivity of addition and multiplication on my funny kinds of functions that are like measurably almost everywhere equal functions. This one, AEQ functions. So you use extensionality, and then what you want to do is you want to sort of just push the coercion inwards. But if you don't have generalized rewriting, this is a bit awkward. So you get this proof that's like 15 lines long. But actually, you can just prove it in one line with with generalized rewriting. So what's going on here? We simply rewrite this coercion inwards. And if you look at the lemma, what it's saying is some statement about almost everywhere equality instead of just normal equality. And so we can now rewrite with this. And so you push the coercion all the way inwards until at the end it's just a normal admol, and then reflexivity, which is implicit at the end, solves the goal. Right. Wait, no, I have one more slide. Future improvements. Right. So we have a bunch of great features, but there's also some edge cases where you would like more things to be done. So one thing, I've implemented a rewrite suggestion tactic, which exists in MATLib, rewrite question mark. You should give it a try. But a similar thing could be done for generalized rewriting, which would, maybe they can be the same tactic. I don't know. Then there's the obvious constraint of rewrite not rewriting under bound variables, but we've seen on the roadmap that this will change. Rewrite will be able to rewrite bound variables. So I will try and, when that happens, port this over to generalized rewriting. And then some other things, like, for example, you can't rewrite where you have a multiplication with a negative thing, because currently we don't have like a negativity tactic, and somehow figuring out whether it's positive or negative is also a bit awkward. So we could try to get that to work. Another detail is the point where grewrite figures out where to actually rewrite. It just sort of tries all of the places at the same time, instead of first looking where it would actually be sensible to rewrite. So this is another thing that could be improved, but only with a major refactor of how the tactic works. And then finally, some people also mentioned this on Zulip, that they would like to see this. So let's say your goal is a plus 1 is less than c, and you know that a is less than b. You can do a generalized rewrite to turn that into b plus 1 is less than c. But actually, it's also mathematically valid to turn it into b plus 1 is less than or equal to c, due to how the strictness of your inequality works. So then it's not technically a pure rewrite anymore, but it still would be useful to be able to do that. So again, possible improvement. Thank you for listening.